Welcome you all to the class of Calculus and Differential Equations 21 MAT11. Today, let us discuss a topic in Module 2, Differential Calculus 2. And the topic that I'm going to discuss today is about Lagrange's method of multipliers with one subsidiary condition. Myself, Dr. Madhura, Assistant Professor, Department of Mathematics, Sai Vidya Institute of Technology, Bengaluru. Lagrange's method. Now first we will know what do we exactly do in this method. So this Lagrange's method of multiplier with one subsidiary condition is a method of obtaining the stationary values of a function of several variables subject to a specified condition. So here we will be finding the stationary values of given function u, which might be a function of x, y, z, subject to the condition phi of x comma y comma z is equal to c, where c is a constant, and the following working rule is employed for that. So let us see the working rule to work problems on Lagrange's multiplier method. So firstly, we form the auxiliary function, denoted by capital F is equal to u of x, y, z plus lambda into the condition given, that is phi of x, y, z. That's a step one for us. In step two, we form the equations fx is equal to 0, fy is equal to 0, fz is equal to 0. Let us recall the notations for fx, fy, and fz. Fx stands for dou f by dou x, partial differentiation of f with respect to x. Similarly, fy stands for dou f by dou y, and fz stands for dou f by dou z. Third condition being, or third working rule says that we solve for x, y, z and lambda. Solve for x, y, z and lambda from the above equations, from these equations, along with phi of x, y, z is equal to c. Along with the given subsidiary condition, phi of x, y, z is equal to c. And the values of u of x, y, z are the stationary values. The values of u of x comma y comma z are the stationary values. So when we solve for x, y, z and lambda, we will be able to obtain the stationary point known as denoted by x comma y comma z, and the values at that particular point, that is u of x comma y comma z, gives us the stationary values. So let us do problems on this method now. Problems. Firstly, find the stationary value of x square y cube z power 4 subject to the condition. The subsidiary condition will be mentioned for us in the question. X plus y plus z is equal to 5. So here we compare the given question with the standard form. we will be having the given function in the form of u of x comma y comma z. So here the function is x square y cube z power 4, which is denoted by u. And the subsidiary condition will be mentioned in the form phi of x, y, z is equal to c. So here the condition is x plus y plus z is equal to phi. So step 1, the working rule says that in step 1, we form the auxiliary function denoted by capital F, and capital F is given by u plus lambda phi form. So before I write down u plus lambda phi form, I'll write down what is u in the given question. So here u of x comma y comma z is equal to x square y cube z power 4, and the condition phi of x y z is equal to c is of the form here x plus y plus phi z is equal to phi. So therefore we frame the function f is equal to u plus lambda phi. So here f is equal to u is nothing but x square y cube z power 4 plus lambda into phi. Phi is x plus y plus z. So this is how we are able to write down the function f first. Now we need to form the equations fx is equal to 0, fy is equal to 0, and fz is equal to 0. So form the equations fx is equal to 0, fy is equal to 0, fz is equal to 0. This is step 2 for us. So dou f by dou x. Differentiating the f function partially with respect to x, with respect to y, and with respect to z, we equate them to 0. So fx is equal to 0 will fetch us 2x y cube z power 4 plus lambda is equal to 0. Fy is equal to 0 will give us 3x square y square z power 4 plus lambda into 1 is equal to 0. And lastly, fz will give us 4 into x square y cube z cube plus lambda into 1 is equal to 0. So this is how we are able to write down the partial derivatives with respect to x, y, and z. Now we need to solve for x, y, z, and lambda. That is what the step 3 says. We need to solve for x, y, z, and lambda and find out the stationary point x, y, z from this. So let us write down what is lambda from each of these equations, and we can equate the pairs. We can consider the pairs from these and try to obtain the expressions for x, y, z. So let us do that further. So from this we can write it down. Lambda is equal to minus 2x y cube z power 4. I'll call this as equation 1. From the second one, I can write down lambda is equal to minus 3x square y square z power 4. We'll call this as equation 2. And finally, from the third one, lambda is minus 4x square y cube z cube. And respectively, I have denoted this by equation 3. Now, we will consider pairs. That is, say equation 1 and 2, we will consider, and we will try to solve for y and z. We will try to solve for y and z. We will try to represent all the variables in terms of x only. Say I will try to substitute or express the expression for y in terms of x. Similarly, z also I will try to express in terms of x. So we are trying to obtain the stationary point x, y, z. So way of doing is left to each individual. So first I will consider the pair 1 and 2. So from equations 1 and 2. From equations 1 and 2. So we have the expression minus 2x y cube z power 4 is equal to minus 3x square y square z power 4. We cancel off the like terms on the left hand and the right hand side. So 1x get cancelled left hand side. Z power 4 get cancelled on both sides. Minus sign gets cancelled. So what do we remain as 2y is equal to 3x. So here we observe that we are able to represent y as 3x divided by 2. So in this expression from the pair 1 and 2, I am able to obtain y as a function of x. So in the same manner, I'll consider another pair, that is from equations, say 2 and 3. From equations 2 and 3, we have minus 3, minus 3x square y square z power 4 is equal to minus 4x square y cube z cube. Is that the equation? Let us check once. So from equations 2 and 3, I'm equating the lambda. So I have RHS is equal to RHS since the LHS are same. So minus 3x square y square z power 4 is equal to minus 4x square y cube z cube. So that is what I have equated. Now again, cancelling of the like terms, x square get cancelled on both sides, y square get cancelled on both sides, z cube get cancelled on both sides, minus gets cancelled. So what do I remain is 3z is equal to 4y. Let us try to substitute for y here. So 4 into 3x divided by 2. As I mentioned, I'm trying to express all the variable, that is y and z, both in terms of x. So we have 4 into 3x divided by 2, which gives us 6x. So we have 3z is equal to 6x, or z is equal to 2x. Z is equal to 2x. So we obtained y in terms of x and we obtained z also in terms of x. We will try to substitute both y and z values into the given condition. The condition is x plus y plus z is equal to 5. So when we substitute in this condition, we will be able to explicitly obtain the values, real values of x, y, z. So substituting y is equal to 3x divided by 2, z is equal to 2x in the condition x plus y plus z is equal to 5. We get, I'll retain x as it is, y is 3x divided by 2, z is 2x, and this is equal to 5. So we will try to simplify this by taking common LCM. 2 is the LCM. Numerator will be 2x plus 3x plus 4x, and that is equal to 5. And this in turn gives us 9x divided by 2 is equal to 5, or x is equal to 10 by 9. X is equal to 10 by 9. So once we know the value of x, we will be easily able to obtain the values of y and z, because y is equal to 3x by 2 and z is equal to 2x we have. And since I already know the value of x, I'll substitute x value in this expression for y and the expression for z to obtain both y and z. So therefore, y is equal to 3x divided by 2 will give us 3 by 2 into 10 by 9. So this simplifies and obtain the value of y as 5 by 3. And also we have z is equal to 2x. So 2 into 10 by 9. And z will be 20 divided by 9. Now I know the stationary point, that is x comma y comma z obtains the or gives us the stationary point for us. That is 10 by 9 comma 5 by 3, 10 by 9 comma 5 by 3 comma 20 by 9 is one of the stationary point. And since we are asked to find the stationary value of x square y cube z power 4, so we will substitute this value in x square y cube z power 4 and obtain the stationary value. Therefore, stationary value of x square y cube z power 4 will be substituting these values, that is 10 by 9 whole square, and we have 5 by 3 whole cube multiplied by 20 by 9 whole power 4. And this on simplification will give us 139.38. can use calculator to obtain the value answer here. So it gives us 139.38 approximately. And this is the stationary value of the given function u of x, y, z is equal to x square y cube z power 4. We'll do another problem on Lagrange's multiplier method. Second question. A rectangular box open at the top is to have a volume of 32 cubic feet. Find its dimensions. Find its dimensions if the total surface area is minimum. We'll try to understand the question. A rectangular box open at the top is to have a volume of 32 cubic feet. So volume of the rectangular box is given for us. And we need to find its dimension if the total surface area. We need to find the dimension means here it is nothing but the stationary point what we'll be finding. So here we need to find out x, y, z, which becomes the dimension of the rectangular box. If the total surface area is minimum, and that is a condition given for us that the total surface area is given to be minimum. So very firstly, if I denote x, y, z respectively as the length, breadth and height of the rectangular box, and v becomes the volume of the rectangular box, and let us assume s to be the total surface area. And from the data, it is given that x, y, z volume is equal to 32. We recall volume of a rectangular box is given by x into y into z. That is length into breadth into height. And that in turn is given to be equal to 32 cubic feet from the given data. And we recall that the total surface area is given by, for a rectangular box, the total surface area is given by 2 times of xy plus yz plus zx. Length into breadth plus breadth into height plus height into length. And since the box is open at the top, the corresponding surface area will be this expression what we wrote as a formula minus of the length into breadth, that is x into y. We'll pen them all now to understand better and write it down. Let x, y, z represent, let x, y, z respectively be the length, breadth and height of the rectangular box. And let us denote V as the volume and S be its surface area. So therefore, by data, we have volume of the rectangular box given to be x into y into z, and that is in turn is equal to 32. And we are familiar with the formula for total surface area, which is given by 2 times of xy plus yz plus zx. Now, since the boxes condition is mentioned here, the box is open at the top, the corresponding surface area will be, the corresponding surface area can be written as S is equal to 2 times of xy plus yz plus zx minus x into y. So consider or just imagine a rectangular box in front of you, and since the box is open at the top, it is a very easy example to recall a geometrical box, which is rectangular in shape. And if we open the box, that is, the top is open, then it will be not considered with length and the breadth of the respective face. So we have minus x into y. So this gives us s is equal to xy plus 2yz plus 2zx. And this we assume as, say, u of x comma y comma z. So now we will be able to write down that our aim is to find x comma y comma z such that S is minimum. S is minimum subject to the condition xyz is equal to 32. So subject to the condition xyz is equal to 32, S is minimum. And with these conditions, we have to find out x, y, and z. To find the dimensions is our aim. So let us first solve this by Lagrange multiplier method by assuming capital F. So capital F function will be u of x, y, z plus lambda into phi. Condition phi here is x into y into z. Now we form the equations fx is equal to 0, fy is equal to 0, and fz is equal to 0. Let us do the partial differentiation with respect to x and obtain y plus 0 plus 2z plus y plus 2z plus lambda into, with respect to x, when we differentiate, we get y into z. So lambda yz is equal to 0. So from this, we will be able to write down the lambda value as minus of y plus 2z the whole divided by y into z. Similarly, we equate fy is equal to 0, means partial differentiation with respect to y. Fy is equal to 0 will give us x plus 2z plus lambda into with respect to y, so xz is equal to 0. So lambda will be minus of x plus 2z the whole divided by x into z. And finally, partial differentiation with respect to z we are doing. So with respect to z, x and y both are constants. Differentiation goes to 0 plus differentiation of z will be 1 into 2y. So 2y plus 2x, 2y plus 2x plus lambda into, with respect to z, when we differentiate x, y, z, we will have x into y constants. Z differentiation becomes 1. So this gives us lambda is equal to minus of 2x plus 2y the whole divided by x into y. So we have LHS equal now, all our lambdas. We can make pairs. We can equate the RHS first and write down the expression. Then we can consider the pairs and do the problem. So first I will equate all the lambdas. And that will fetch me minus of y plus 2z divided by yz is equal to minus of x plus 2z divided by xz is equal to minus of 2x plus 2y the whole divided by x into y. So we can cancel minus throughout. Now we will consider the pairs from this. So from the first and the second term, I am equating the first and second term and trying to represent y and z both in terms of the variable x. To do that, First, I will consider the first and the second term, cancelling of the minus sign. So y plus 2z divided by yz is equal to x plus 2z divided by xz. So z get cancelled in the denominator. Cross multiplying the remaining terms, we have xy plus 2xz is equal to xy plus 2yz. So again, xy get cancelled. We have 2xz is equal to 2yz. 2 get cancelled, z get cancelled. We have x is equal to y. Or the same I will represent as y is equal to x. Means we have tried to represent y in terms of x now. In the same manner, considering another pair, either the second and the third term you can consider, or first and the third term you can consider. So considering another pair, we will try to represent z also in terms of x. We will try to represent z as well in terms of x. So to do that, I will consider the second and the third pair. However, the way you want, you can do it. I'm considering here second and third term. By cancelling of minus sign, I consider the terms x plus 2z divided by xz is equal to 2x plus 2y divided by xy. So we observe the denominator, x gets cancelled. Cross multiplying, we obtain xy plus 2yz is equal to 2xz plus 2yz. 2yz get cancelled on both sides. We have xy is equal to 2xz, or cancelling xy will be 2z. So since y is equal to 2z, we can write down z is equal to y by 2 from this. And since y is equal to x, we have already obtained y is equal to x, no? So substituting that, I can obtain z is equal to x divided by 2. So our aim is to represent both y and z in terms of x, so that we are trying to represent with respect to one single variable, which in turn will help us to obtain the stationary point x, y, z respectively. So now we substitute x, y is equal to x and z is equal to x by 2 in the given condition. Here the given condition is with respect to the volume of the rectangular box. So it is x, y, z is equal to 32. This is the given condition here for us. So here we are going to substitute the value of y and z in terms of x. So substitute y is equal to x and z is equal to x by 2 in the condition, and the condition here is x, y, z is equal to 32. 32. We are trying to obtain in this, substitute in this. So we get x into y is nothing but x itself, z is x by 2 is equal to 32. So cross multiplying 2 to the other side, x cube is equal to 64. Neglecting the complex roots, we obtain the real root from this as x is equal to 4. 4 4s are 16, 16 4s are 64. So when I take cube root, I'll be getting the real value as x is equal to 4. Here we neglect the complex roots. We are neglecting the complex roots here. Okay. Now, since x is equal to 4, we have, since y is equal to x, this gives us y also as 4. And z is equal to x by 2, which is 4 by 2 gives us z is equal to 2. Thus, the dimensions of the rectangular box such that S is assumed to be minimum are 4, 4, 2. Hence the solution for this. So hope these problems on Lagrange's multiplier method of with one subsidiary condition was helpful to understand. All the problems of this method remains on the same methodology, that you are going to consider the function f first, which is u of xyz plus lambda into phi, phi being the condition, subsidiary condition given for us. We form the equations fx is equal to 0, fy is equal to 0, fz is equal to 0, and solve for x, z, and lambda. Then, if at all you want to obtain the u of xyz value, the stationary value or the minimum value or maximum value, you substitute xyz into that expression u, and hence you will be obtaining the minimum value, the maximum value, whichever has been asked to us. Thank you for watching.